So, what are we studying this unit? Boom, one sample test of hypotheses. Hypothesis testing is what we're studying, okay? For chapter 10, all right? So it's a complete new chapter, change the subject. Everybody understand me? But, fortunately, it's nothing we haven't seen before, all right? All we're going to be doing this chapter is using the stuff that we've looked at already, okay? In chapters 8 and 9 and putting it together in a different way, okay? But literally, there's no new formulas and there's no new math at all, okay? No new tables, that's what I was thinking, okay? All right, so hypothesis testing. So my first question to you in this chapter is, what is a hypothesis? What is a hypothesis? What are we talking about, huh?
A statement about a population parameter subject to verification.
That's really well put. Did you just think of that?
Yeah, man. Just off the top of my head.
That's a good way to put it. So what is that first part right there? A statement? A statement. It's a statement, isn't it? Okay, would this be a statement? At least 10,000 cars a day pass Dalton State on I-75. Is that a statement? That is a statement, is it not?
Mhm.
Is that a statement about a population?
Yep, because it's at least that many.
Right, and I'm talking about all the cars that pass in the day, aren't I?
Mhm.
All right, so that statement I made crosses those first two criteria off for being a hypothesis. What about the third one? What's the third part of that? Subject to verification. What does that mean? Subject to verification. How do you verify something?
You got to test it.
You got to test it, don't you? You got to run tests against it, don't you? And see if it's true or not. Okay? Now I'm going to tell you right now, our hypotheses, just like when I just ran across you, the cars out here in front of Dalton. What do we do if we do the math in this thing and we think that that sucker's wrong? We do what? We reject that hypothesis, okay? So what we're going to be skipping ahead a little bit. Let's get into this a little bit. Here's a couple examples, okay, of hypotheses. The mean speed of automobiles passing milepost 150 on the West Virginia Turnpike is 68 miles an hour. Now we're talking about all automobiles passing that milepost 150, aren't we? Did we study every single car that's ever passed miles down 150?
Yeah.
How did we get that information? We took a sample, didn't we? Okay, so we're still using samples to infer about a population, aren't we? Okay? And again, we're going to be using the same techniques, same mathematical techniques and methods, okay? Like I said, though, we're just going to be putting them in one way or the other to decide whether that hypothesis, whether the hypothesis we have is true or not, okay? That's big picture what we're doing here, okay? Again, deciding whether that hypothesis is true or not based on mathematical testing, okay? That's what we're doing. The mean cost to remodel a kitchen is 20 grand. Did we talk to everybody who's ever remodeled a kitchen? We took a what? Sample, didn't we? Okay. Here's another nice thing about this chapter. In addition to already knowing how to do all the math, there's a process for this, okay? There is a step-by-step procedure to walk through, okay? There's no guessing, there's no ambiguity. Everybody understand me? It's the same process every time, isn't it? So you can ask yourself a series of questions and work through every single one of these problems. Another good thing, really quickly, there's not a lot of math involved in this, okay? But what there is a lot of is reading comprehension, is understanding what you're being asked, okay? Which is easier said than done sometimes, isn't it? Especially with this book, huh? Okay? All right, but we said a hypothesis is subject to testing, didn't we? So what are we talking about doing this chapter? Hypothesis testing, all right? The objective of hypothesis testing is to verify the validity of a statement about a population. That's what we were just talking about, right? Okay, so hypothesis testing. A procedure, a set process, isn't it? A set, what am I trying to say? Order of steps, right? Okay. Based on what? Sample evidence. So again, we're in inferential statistics, aren't we? We can't look at the whole population for whatever reason. Best reason being what? We don't need to. We got good methods to not have to do it, all right? So we're still taking samples, aren't we? Okay? Now, and probability theory, which that's what we've been studying, right, since chapter 5. Yeah, especially in chapter 5 and 7. Okay? To determine whether the hypothesis is a reasonable statement. That's all we're doing. Okay, now, when I say that, when I say we're looking at a sample and using our probability theory to determine whether a hypothesis is a reasonable statement, did I say we're trying to prove a hypothesis?
No.
I did not, did I? I said we're trying to find out if it's reasonable or not. Think of it this way. Last time you went to court for that bag of drugs they found on you, remember that? Yeah, everybody remember that?
Yeah.
Just trying to see who would nod their head. Anyway, when you were tried, were they trying you to find you innocent or guilty? No. You probably would have cut a deal and narked on your dealer, knowing you people. I'm just kidding. That's what you should do. All right, but what are they trying to do? When you go to court and you're on trial, are you found innocent or guilty? You're found guilty or what?
Not guilty.
Or not guilty, right? But you're never found innocent, are you? Everybody understand what I'm saying? Okay, so we're not trying to prove our hypothesis. All right? What we're trying to do is reject our hypothesis or not reject our hypothesis. Does everybody understand what I'm saying here? Okay, and what is our hypothesis? Our hypothesis is that statement, a truth about the world as we believe it. Everybody understand what I'm saying?
Gotcha.
Okay, and what the 10,000 foot view of what we're doing here is we're going to have a hypothesis, okay? And we're going to say, we're going to do the math with variables given to us. We're going to walk it through these steps, okay? This is the math. The math is in these steps, okay? And we're going to use our probability theory that we learned, and we're going to say, okay, this hypothesis we have, does it hold true all the way through these steps? Or are we going to reject that hypothesis? Okay? That's what we're saying here. Does everybody understand what we're doing here? Okay?
So,
Again, we're not going to prove that hypothesis. We're not going to prove that 10,000 cars pass or more pass in front of Dalton State. But what we're going to say is it's reasonable that that could be the case. Therefore, we cannot reject our hypothesis. But if we somehow we walk it through these steps and we come up with an answer telling us that there's no way 10,000 cars are driving out here in front of Dalton every day, we're going to reject it. Our hypothesis, aren't we? We're going to say, nope, can't be true, reject it. Okay? That is what we're doing here. Everybody with me?
so basically your process is your bouncer and your hypothesis is the people trying to get in the club and they either let them in or out. Got you.
Yeah, what he said.
That's right.
Yeah, I guess so.
Basically. Might as well be.
So the process is, yeah, we'll kick it out or we'll reject it, right?
You either let it in or you kick it out.
There you go. But you're never proving it, right?
That's right.
Which I don't know where that comes into play there. I like my courtroom analogy better.
Yeah, courtroom is much, much better.
This is the judge,
That's right.
okay? And the judge is gonna find it guilty or, this is the jury. Judge and the jury. Like me in this classroom. But
Especially
just
the
kidding.
judge.
I'm not trying to
Dredd.
power trip on anybody. Huh?
That's Judge Dredd right there.
Judge Dredd?
Yeah, straight up.
I think more like Judge Judy.
Well, same thing,
Hmm.
basically. You got a lot of super shots now.
They got Judge Jerry now.
Judge Jerry? Not Jerry Springer. No, he's a judge now. What?
Yeah, I seen it on the TV the other day.
Oh my gosh, that's gonna be the show to end all shows right there. I gotta see that one.
Judge Jerry and RoboCop, there we go.
He's been in front of a few judges in his day.
Mm-hmm.
You know what I'm talking about? Y'all should look up what he did. He was the mayor of Cincinnati, Ohio. Did you know that? Until he did something really funny, but really stupid. That I'm not gonna mention in front of a camera. All right? All right.
Thanks for recording, I forget about that.
Yeah.
Hey guys, how y'all doing?
Don't worry. If I need to edit it, I'll put a note.
You have captions.
Yeah, that's I put it in the title when I downloaded it to the computer. I say, need to edit in caps. Like last week. All right, so step 1 of the 6-step process. So again, the beauty of this thing is it's a process. Every time it's the same. All right, so step 1, all we're going to do is say, what's our hypothesis? Sounds pretty easy. Like I said, there ain't all that much math to this. But you got to be able to understand what the problem is, okay? And what is all this junk up here about your null and alternate hypothesis? Okay, so a null hypothesis is the statement about the value of a population parameter developed for the purpose of testing numerical evidence. The null hypothesis is what you think is going on right now, okay? That is your hypothesis. That is like what we think the status quo is. For instance, I think that there's 10,000 or more cars passing in front of Dalton State every day on I-75, okay? That's my null hypothesis. That's what I believe is going on in the real world, the status quo, okay? Everybody follow me? All right, well, let me ask you this. So I'm going to write it like this. I call it the ho-ha, okay? But they call it HOH1. So this is alternative, okay? A, same as 1, doesn't matter, okay? So, how would I write that about the cars out here? What would I say? The average population of a car, of number of cars passing Dalton State every day is at least 10,000. How would we write that in words? Well, could we write it like this? The mean, the population mean, all the cars passing in front of Dalton, is greater than, or equal to, very good. What?
10,000.
10,000. Does everybody see that? That is the mathematical expression of what I said in English, isn't it? Everybody understand? Everybody with me? Okay? Now what is the only other thing it could possibly be? So if it's not 10,000 or more, as in what we believe it is, what's the only other thing it could be?
Less than 10,000.
Very good, less than 10,000. So that would be our alternate hypothesis, wouldn't it? De facto. There's nothing really to figure out about it. It's all that's left, isn't there? Okay? Fortunately for us, though, it's always going to be opposite. Okay? So if you don't understand that idea, then just remember to flip that sucker backwards. And they're going to look like this every time. This is how we're going to write our null and alternate hypotheses every time, okay? Literally every time. And I don't want to have to take up scratch paper, but I will if I have to, if people aren't writing their variables, writing their formulas, and writing their graphs. Okay? Now, so what are we saying right here? Read this to me in English. The null hypothesis is what?
The population is greater than or equal to 10,000.
The population what?
Size.
No.
Or,
Huh? The size would be that, wouldn't it?
yeah.
Me.
What?
Me. Yeah.
Mean. Gird.
So the population mean of cars passing in front of Dalton State every day is greater than or equal to 10,000, isn't it? Conversely, the only other thing that could be possibly happening is that the mean is less than 10,000 cars. All right, we good? All right. That's step number 1. Believe it or not, it's that easy. Identifying what our hypothesis is, null hypothesis, writing that as our null hypothesis, and identifying the alternate. Okay? Now I want you to notice something right here. The null hypothesis always includes the equal sign, equality in some form or function. Okay, so what are my conditional operators? Who remembers? Not conditionals, but my, what do you call those? My comparative operators. What are they? There's only 6 of them, and we're looking at 2 of them. So there's greater than, less than, or what?
Equal to.
Equal to. Very good.
And then there's
What's the opposite of equal to?
not equal.
Not equal to. And what are the variations of this one?
That's greater than or equal to.
Greater than or equal to, and what? less than or equal to, and that's all we have, isn't it? Okay, so do you see how there's equality represented in each one of these? There's the equal sign represented in here in some way in each one of these, isn't there? Greater than or equal to, less than or equal to, or just straight up equal to, isn't it? Okay? This is always going to be the HO, the null hypothesis, okay? Is going to have one of those three. Notice right here we're saying that the mean is greater than or equal to 10,000 cars, aren't we? The alternate hypothesis will never have the sign of equality there, okay? It'll always be greater than, less than, or not equal to. That's all it'll ever be. And whatever it is, it'll be the opposite of what we had in the null hypothesis. Okay? What I'm saying is if the null hypothesis is that, the alternate will be that, won't it? If the null hypothesis is that, the alternate will be that, won't it? And if the null hypothesis is that, the alternate will be that. Everybody see what I'm saying? It's the opposite, just without the equal sign. Okay? So does everybody understand what we're doing here? There's no math involved at this point, is there? All we're saying is, this is what we believe to be true, and this is what it will be if what we believe is not true. Everybody good? All right. Blah, blah. All right, we're moving. Good job. So that's step one. Pretty easy, huh? All right, step two. Now all we have to do is select a level of significance. Does everybody remember doing that? You shouldn't, because we haven't done it yet. Well, most of us haven't. I don't think you have either. You were gone by now, aren't you? No, I'm just kidding. All right. So, what are we talking about here with the level of significance? Okay. First off, what's not on the board here? Okay. The probability of rejecting the null hypothesis when it's true. Okay. That doesn't make any sense right now, does it? But I'm about to show you why that does make sense, or what that means. Okay. So this is a normal bell curve, isn't it? Right there? Does everybody see that? We've seen these before, haven't we? Okay. Let's say that we want to be 95% sure about something. Remember doing that kind of stuff? What does that leave for the rest of the curve? 95% sure,
5%.
5% for the rest of it, doesn't it? And let's just say, this is just an example, okay? There's no math behind this. I'm just trying 10,000 foot view again, okay? Let's just say that that's the 5% that we're not sure about, okay? All right. So what we're doing here is we haven't done the math yet, but when we do the math, okay, and we're going to get a number, and it's going to look like one of your standard deviation numbers. It's going to be a z, okay? All right. If that number lands over in here, we are going to reject the null hypothesis, okay? If it lands in that shaded area, we're going to say, well, you're not true, you're true, okay? If it lands over here in the non-shaded area, we're going to say, hey, I didn't prove that you're true, but I didn't prove that you're unreasonable either. So I'm not going to reject it, right? Everybody understand how that's kind of intuitive, isn't it? Because if the null hypothesis is true, we would expect it to land in this big area somewhere, wouldn't we? But if the null hypothesis is not true, we would do the math and get something way out here in the shaded area, wouldn't we? Because this is actually true. That's why we got an answer way out here. Not within the area where it should fall if it is true. Okay? Now, this shaded area right here, this 5%, is called your alpha. Okay? Everybody with me? The alpha will be given to you in your problems for academic purposes, okay? The problem will tell you with an alpha of whatever, okay? Here's the guideline, okay? 0.05 is used for customer research projects. Alpha of 0.05 or 5% of the area under the curve shaded, yeah? .01 for quality assurance, because what are we talking about there? Why would we use .01 for quality assurance? Because what are we talking about? We're talking about,
1%.
yeah, because we're talking about manufacturing type stuff, aren't we? So in manufacturing, we got the same processes rolling through every time, don't we? So we want very little error in there, don't we? Okay? And what about for political polling?
10%.
An alpha .1, huh? Okay. Where are we usually going to be for this class?
0.5.
0.05, yeah.
0.5.
5%. Everybody good? All right. So do we know what alpha is? It's that shaded area, okay? And that shaded area says if the null hypothesis is right, then when you do your math, it ain't gonna land in me in the shaded area. Because the odds are really low that you're gonna land in me if your null hypothesis is correct. Okay? In fact, if that alpha right there is 0.05, what are the odds of this being correct and it landing over here?
No.
5%, 0.05, right?
Yeah, that's right.
So there's a very low percentage that it'll land in the shaded area if it is correct. However, 5% of the time it will do that. That is what we call a type 1 error, okay? Now, just because it's called an error doesn't mean you did anything wrong. It's just that 5% of the time, it's going to fall in there when it shouldn't, okay? Does everybody understand me? You just need to be able to identify what these errors are. There's a type 1 error and a type 2 error, okay? Type 2 errors are called beta, okay? Represented by the Greek beta. Type 1 errors are what we're talking about here with alpha, okay? I really like this chart right here. Let's give it a look, okay? You're going to have these slides, so. Okay, so the null hypothesis is down the rows, right? Or the different outcomes for the null hypothesis. And across the top we have what? What you do with it. Either reject it or don't reject it. What is this called when we have two variables and we run them across each other? Contingency table. Yeah, remember that? Okay. All right, so null hypothesis. If the null hypothesis is true and we reject the null hypothesis, i.e., this null hypothesis is true, we did the math correctly, it still landed out here in the shaded area, so we're like, we reject that null hypothesis, okay? But it's true. The null hypothesis is true. We committed a type 1 error, okay? Now with an alpha of 0.05, that's going to happen 5% of the time, isn't it? Okay?
So when we reject it, it's the error.
When you reject it, what?
When we reject it, it's the error. It's true, but since we rejected it,
So when you reject it, but this is true. So usually if this is true and you do your math, then your z-score, let's say we're using a z-score, will fall in here in the non-shaded area, right? But with an alpha, if our alpha say equals 0.05, this is 95% of the curve, right? So 95% of the time that it'll hold true. 5% of the time though, you'll be wrong, okay? You got to be able to recognize that. All right? Now, if the null hypothesis is true and we don't reject the null hypothesis, that's the correct decision, isn't it? We don't want to reject it if it's true. This is real world stuff, isn't it? This is the 10,000 car thing. All right? We'll flip that around for the type 2 error, which we'll look at later after we do our p-values. I don't know if you've ever heard of that, but we'll look at it tomorrow or Thursday. All right. So if the null hypothesis is false and we don't reject the null, okay, meaning this in the real world, this thing is false. We should reject it, but we don't. That's a type 2 error, okay? But if if this sucker is false and we do reject it, then that's how it should work, okay? Is everybody following right here? All you'll need to be able to do is identify those, type 1 and type 2 errors, okay? I know it's easy to flip around, but just take 5 minutes and look at it and get to know it, and you'll be fine. All right? Now, on to step 3. Ready? Are we good? Who's not good? Who's lying? Who's like, what is this dude talking about? Most everybody.
Yeah.
Who's going to the fall fair today? The fall festival? Are you with your kids and everything?
They're there right now.
Oh, are they really?
There's a festival.
Some father you are, just leaving your kids. I'm just kidding. I'm just
I
kidding,
can go
dude. I'm
right
just
now.
kidding. I'm teasing. I'm teasing. I'm teasing.
I didn't know there was a festival.
Yes. What is it? The Fall Family Festival or something like that? It's out. Where's it at? Out here in front of the clock, right?
I'm not sure where it's at. I'm gonna call them afterwards.
In the quad over there, in front of the clock tower.
Well, dang,
And free food? Is it food?
Does it go till after 7:30?
Huh?
Does it go till after 7:30?
Yeah. How long does it last? What's the time on it?
I think it ends at 8.
8.
I might give you a little something because that's when I get out. So, all right.
Yeah. Maybe I'll go over there.
If I get out here early, though, I can get over there.
No, you ain't not early. Forget that. I'm not into that family stuff.
You're
I don't have a
you're
family,
not
so
a
why
family
should I
stuff.
make accommodation for other people's families? That's what I want to know. What?
Never mind. I would say something. I'm good. Continue.
You don't have a family either. What do you care?
I don't. I was like to mess with other people's families.
Just wrecking them? All right.
Anyways, continue.
So, we go with that then. All right. On to step 3. We ready?
I hope you forget to edit this video.
No. That won't happen. Trust me. All right. On to step 3. The problem is I have to watch it all again. All right. Note to self. Edit before step 3. Now we got to find the test statistic, okay? And this is the Z. That's all we're talking about right here. We're figuring out where this sucker falls. Pretty intuitive, isn't it? That makes sense if that's the next logical step, doesn't it? All right, I said we're using a Z. Have we seen this formula before? We have, haven't we? What does this say right here? Testing a mean. What does that say?
Sigma known.
Sigma known. What does that mean? What is sigma?
You know what your standard dev is for your population.
Very good. You know the standard deviation of the population, don't you? Therefore, we use the t-test, right? No. What do we use? The z, if we know the sigma, don't we?
Oh, yeah. that's
If
right.
we don't know sigma, what do we use instead of sigma? What do we use?
Use your S.
S. Very good. We use the standard deviation of our sample that we took, right? As the best point estimate that we have, isn't it? But we always want to use the population data if we have it, don't we? Because the whole gist of what we're doing is trying to figure out about the population. So if we have population data, let's use that, right? But if we don't, we have to substitute in the best data we have, which is our sample data, okay? But if we use the S instead of the sigma right here, we can't use what? Z, very good. We have a t-test, don't we? Okay? But in this one, we know the standard deviation of the population, don't we? All right? We good? So the test statistic, a value determined by the sample information. So again, remember, we are taking a sample to test this thing, aren't we? Used to determine whether to reject the null hypothesis or not. This is really what it all comes down to. We're going to figure for that z. We're going to be given all these variables in our problems. We're going to straight plug them in, figure a z, and then we're going to find where the z falls on this thing. Well, we know that's 0, don't we? Right there in the middle on the z-score table. Remember that? We reset the mean, median, mode to 0, don't we? Okay. And these are all going to look like your normal standard deviations, aren't they? I.e. 0 to 3 somewhere. Okay? All right. But let's say right here that we do this math. Okay? let's say we have a sample that's given to us in a problem, and we have the population data that's given us to us in a problem, and we come up with z equals 1.83, let's say. I just made this math up, okay? 1.83. Okay, so we know this is 0, yeah? It's not there anymore. We know this is 0, don't we? So where does z, we know it's going to be positive. It's positive 1.83, okay? Does it fall in the shaded area or to the left of the shaded area? Where does 1.83 fall right there? Huh?
It'll be just to the left of it, right? Because you're within 2 standard deviations.
Well, why 2 standard deviations? What does that have to do with anything?
Well, that's true. I guess from that one side, though.
Right, because this is one side. But let me ask you something real quick. Let me ask y'all something real quick. So, what do we need to know in order to know where this sucker falls?
You need to find your your chart. You gotta go to your Z chart, right?
Yes, we will. Yes, we will. Okay, but more intuitively, what do we have right here? We got a line dividing what? The shaded area from the non-shaded area. Our alpha from the rest of it, don't we? Okay, we know this is 5%, don't we? We know we have an alpha of 0.05, right? And we know this is 95%. So let me ask you something real quick. What is this right here? That's 50% of this thing. What is this all the way to the end? 50%. Remember, it's a normal curve, isn't it? How are we going to divide this 50% up, though? If that's 5%, how much is here to here?
45.
45%, isn't it? Everybody with me? So now you tell me, somebody's already hit on it right here, how would we find where that line is right there? What do we have to find that line? Well, we got an area under the normal curve, don't we? What can we do to find where that line is that separates our alpha from the rest of the curve, area under the curve? Huh? Very good. Use your z-score chart. Why do you think of that?
I don't know.
How do we do that?
With our eyes.
Huh? Close your eyes and just pick up. there you go. It's worked so far. We go to our book, don't we?
That is correct.
Unless you're on the test, then you're going to have a copy of this, aren't you? So we go to our book. And we don't go to this one, we go down to page 762, right? You have a hard copy? Oh, I thought you were flipping through the book over there. Did anybody buy a hard copy of the book?
Nope.
You did? This hasn't come in handy? I like having a hard copy too. And it should be the same table in the back, isn't it? What edition did you get? Oh, that's the current one. Okay. All right, right on. All right. Somebody's rich over here, huh? No, I'm just kidding.
No, I'm not getting paid for.
I'm just, oh, there you go. That'll work too. All right, so if we know, first off, how do we use this table? Are we going to find the 5%? Do we start over here and come this way? Where do we start from? The middle and work out, don't we, when we use this chart? What area do we need to find? Huh? 45%. We need to find this to that, and that'll give us the z-score for that line. Now we know our z value is 1.83. We need to compare that to what we find for this, don't we? So y'all show me where to stop here. I'm trying to find 45%, right?
Well, keep coming down.
Keep going down. Well, there's 47.5, so,
Go up a little bit.
so I need to go up
Yeah, just a little bit. And then
to here,
to the left.
to here,
Nope, too far left. A little more. No, right.
more
Yeah.
left,
No,
to
no,
there?
No, no, no.
More right?
Your other left.
more right.
Yes.
Like this way?
Perfect.
45, 45. Okay, so we're looking at 1 point. Oh, wait a minute. No, I don't agree with that. I think we're going right here. Man, you're off today.
I know.
I'm just kidding. All right. So 45 would be where? Wouldn't it be right here, right between these two? 44.95 and 45.05? So I'm going to say it's 1.6 what? 45, so I'm gonna round it to 1.65. Okay? Sounds familiar, doesn't it?
Well, 1.83 is a little bit bigger.
Sims are 90, huh? We'll look at it in a minute.
Yeah.
All right, so this is what? 1.65, isn't it? Where did I find that? Well, I know that from here to there is 45% of this area under this half of the curve, right? And so I went to, oh, it's not on there. I went to 45, which is like right here, isn't it? 43, 44, 44.95, 40, oops, I hopped over it. It's actually right in the middle of these two, isn't it? So I'm looking at 1.6 and 4 or 5, so it's 5, yeah? Okay. So now I know that this right here is 1.65. What should we call that line right there? Let's call it the critical value, okay? The CV. Now, we have a z-score of 1.83, don't we? We figured that by plugging all those numbers into our formula that were given to us in the problem. We determined from the table that our critical value is 1.65. Now can you tell me where that z-value goes?
In the 5%.
Huh?
In the 5%.
It's inside it, isn't it? Why is that?
Because it's above the CV.
Yeah, because 1.83 is bigger than 1.65, isn't it? It's over here, isn't it? So we're in that shaded area, aren't we? Therefore, do we reject this null hypothesis or no? We reject this sucker, don't we? Boom! It's in the rejection range. And we accept this alternate hypothesis that, hey, less than 10,000 cars are passing in front of Dalton every day on the I-75, don't we? Everybody see that? Why did we reject it? Because where did it fall? Out here in the shaded area. And why though does that mean we reject it? Just because it's in the shaded area? Because what? Because if this null hypothesis had actually been true, there's only a 5% chance that when we did this math, that z-value would have fallen into here, if that were true. So we're going to say this isn't true.
So there's a 5% chance you made a mistake.
Also. But there's also that chance that you made the mistake. But don't worry about that, because the way that's going to be presented to you in this book is what kind of error is this? You see what I'm saying?
Yeah. That's just saying that if it does land out in your alpha, then if you don't accept the hypotenuse,
The null, the alternate hypothesis.
the null. If you don't accept the null and you accept the alternative, that means you're 95% covered.
Right.
There's a 5% chance that, yeah, you're wrong.
Yeah, there's a chance, 5% out here, but
95% of the time,
95.
if you're in that area,
right.
it's
It works
just
both
bad.
ways, see? There's the chance that it's that much off, but also 95% of the time it's right, isn't it? Okay? See what I'm saying? And by the way, what we'll get to next is looking at exactly how right or wrong it probably is, okay? We'll be looking at the p-values, so it's really not that tough, we're just talking about that, where it precisely falls, okay? And then that area from there to there, okay? But we'll get to that later. By the way, what we just did, what we just did, got it open, don't I? Is step 4. So we've already taken care of steps 1 through 4 of the 6-step process, okay? And we've only had to do math really once, plugging all that stuff into our z-score formula. And then we had to go to the table once to figure out what that critical value was, and that was it, wasn't it? We had to understand what we were talking about, first off. We had to understand the question, and that's the hard, and set it up. That's the hard part. Once you get past there, we got that process to walk through, don't we? Step by step. Okay? Now, so that's what we just talked about. Everybody good with that? You'll have these slides if you don't understand, but... Oh, and steps 5 and 6, this is the rest of it? Are you serious? So, make a decision. Huh? Well, we already did that, didn't we? We made the decision to do what? Reject or not reject the null hypothesis?
Reject.
Reject that null hypothesis, didn't we? And step 6, we interpreted the results, didn't we? What did we say? That there's a 95% chance that if that null hypothesis were true, it would have landed where? Over here, in the non-shaded area, wouldn't it? But it landed in that shaded area. Therefore, we're going to say, nope, not true. Very little chance that if that were true, when we plugged all that data in, it would have landed over here.
It's
And it
unreasonable.
did. It's not reasonable to consider that a possibility, is it?
That's a better way of looking at it, I think, because with the whole 5%, it's like, okay, if it doesn't land there, then it's reasonable, but if it does land in there, then it's unreasonable. Even though there's a 5% chance that you're right.
Yeah.
That 5% is
It's
not
really-
enough to call it reasonable.
Yeah, you wouldn't bet the farm on it.
Exactly.
Yeah.
That's right.
But would you bet the farm on 95%?
Shoot, yeah. Well,
Depends on what you're getting out of that, right?
that's true, you know, if it was like you're getting a horse, I'm like, never mind. But if they're gonna give me about 3 or 4 new tractors, I'd be like, hell yeah.
Yeah, there you go, see? And then if you lose your land, you don't need the tractors anyway, right?
Exactly. So I'm-
Either way, you're good.
Good.
Alright. We good?
Yeah.
So that's the 6-step process for testing a hypothesis. Do you think this is useful in a business context?
Shoot, yeah.
Who's ever seen this in a science class before? Huh? Y'all never seen this in context of like your science, biology, special classes? Scientific method where you actually test the hypothesis. You know,
Yeah.
hypotheses, that's what science is built off of, right? You make a statement, you test it.
That's kind of like saying such and such will happen if I do this, and then you do it, and it either does or doesn't happen.
Right.
Yeah. We've done that before.
Okay. So we're going to do an example before we get out of here, okay? But before I even write anything down, before I even start this example, I want to know what are we going to do every time? We're going to write what?
No.
Our variables. Well, yeah, we're going to do that too, but I mean just every problem, not just these kind of problems. What are we going to do?
Your mean and standard deviation.
We want to know our mean standard deviation, which are what? Variables. Just ate 2 Reese's Pieces, Reese's Cups. The peanut butter sticking in my throat. All right. That's why I brought my water. All right. They're variables, aren't they? Mean and standard deviation are variables, aren't they? So we're going to write our variables down and we're going to draw what? All our graphs out, aren't we? Because this stuff gets too complicated now at this point. It gets too complicated if we're not drawing it, okay? Because there's one more little wrinkle I still have to show you about too. And remember that Greek and Latin stuff? Well, it's important now, isn't it? Because we got these formulas pulling from all over the place, don't we? So you need to be able to identify whether you need to use that sample mean or population mean, or is that the population standard deviation? Oh yeah, so I need to use the Z, yeah? Okay. Right. What is that? Okay. Now there's one little extra wrinkle here. I shouldn't have erased it yet, but you saw in our graph here, we had that data front loaded, didn't we? We had it like this, didn't we? And remember that was our alpha over here, and it was A equals 0.05.
Yeah.
Remember that? And it was all right here, wasn't it, on this side? Why was it on that side, do you think, and why wasn't it down here?
Because it was a one-tail test. You wanted so much, you didn't want like a certain amount over, a certain amount under.
Okay, very good. All right, so we have what are called one-tailed versus two-tailed tests, okay? Now remember this, I wish I had erased all this, I wasn't thinking. But anyway, we got this right here, we got this one, and we have not equals to, don't we? And these are for our alternate hypotheses, yeah? And for our null hypotheses, we have that nature of equality, don't we, in here? Remember that? Okay. So let's look at these 3 examples right here and see if what we've been talking about holds true with these examples, all right? So what is this first one? Let's pretend like this is a mean, like a population mean is what we're talking about, because they don't list it here. What's our alternate hypothesis right there? That the mean is what? Huh? What's our HO there? Mean is what?
than or equal to 60,000 miles.
Very good. Greater than or equal to 60,000 miles. So let's pretend like we're talking about a tire here. What would the null hypothesis be? The problem would read something like this. The Michelin Overland Explorer tire lasts at least 60,000 miles. So what does that mean? At least 60,000 miles.
60,000 or more miles.
60,000 miles or more, right? So greater than or equal to 60,000, isn't it? So that would be my null hypothesis. That's my hypothesis statement. It'd be written like that. But actually, we'd write mean right there, wouldn't we? Like we had it, remember? We want to be a little more exact. Okay. What would the alternate to that be? Anything less than 60. If it doesn't last 60 or more, then it lasts less than 60, doesn't it? That's my alternate hypothesis. So we've been assigned an alpha of 0.05 for this problem, okay? Now, why in this one, remember our example, we had all that data in the front end up there. Why in this example right here do we have our alpha way down here on the left side?
Because you're talking, that's less than what you want.
Very good. So what we're talking about is if our null hypothesis is correct, our z-value is going to fall up here, isn't it? We're going to reject it if it's down here in the way less than and less than, isn't it? Okay? If you don't understand that way of looking at it, just remember, your Pac-Man up here in your null hypothesis is eating towards the shaded area. So null hypothesis is pointed away, eating towards the shaded area, okay? And it always has the equal sign in there too, doesn't it? Okay? Let's look at this one too. Let's say Teddy Grahams cereal has less than or equal to 453 grams of sugar. Okay? What would be the alternate hypothesis to that? The average amount of sugar is what?
Greater than.
Greater than 453 grams. Okay? Again, an alpha of 0.05, why would that be a right-tailed test over there?
Because you want less than that amount.
Yeah, so if our null hypothesis is correct, our z-value is going to fall in here, isn't it? If it falls way up here in this positive area, we're rejecting that sucker, aren't we?
That's right.
Okay? But again, we also have the and less than, so we're not talking about limiting it to the lesser side, are we? We're talking about limiting it to the greater side, aren't we? Okay? But let's look at this one in the middle. What does this one say?
Equals 65,000 per year.
So the mean salary of starting managers at Shaw is $65,000 a year. What is the alternate hypothesis to that? The mean salary of starting managers at Shaw is what?
Does not equal.
Is not anything else. Anything else does not equal $65,000 a year. Okay? So, with an alpha of 0.05, the same alpha, we have a two-tailed test here. Why is that two-tailed? Why is it two-tailed, do you think?
Because you don't want to be above or under.
Right, we're interested in this 95%, which is the complement to the alpha, right? How sure we're going to be, okay, of not 0.05%, but we can't be above it, too far above it, or too far below it without rejecting it, can we? We can't be out of this 95% range either way, can we? Before we reject it. See what I'm saying? Now saying that, what do we have to do to that alpha? So if our alpha is 0.05 here, and that whole 0.05 is concentrated in the shadow, in the shaded area, right? Over here it's all concentrated in this shaded area. What do we have to do with that shaded area, with the alpha? Very good, we have to divide it in two, don't we? Does everybody see what I'm saying here? We're looking at the alpha, but what we're really interested in is the non-shaded area, aren't we? That's where we're thinking this sucker's going to fall. So we got to split that alpha into two, don't we? All that over there and all that over there. So it's 0.05 divided by 2, 0.025 for the two-tailed test. So when you have equals in your null hypothesis, it's a two-tailed test, isn't it? When you have greater than or equal to, we're talking about this area over here, aren't we? For the alpha, where we think it's going to land is up here. And then if we have less than or equal to for our null hypothesis, we're talking about this area up here because we're thinking there's a 95% chance that if that null hypothesis is correct, it's going to land over here and not in the shaded area. This is out of bounds for us, isn't it? Because we know if it lands up there, we're going to reject this null hypothesis because there's a very tiny chance that if that null hypothesis is correct, it's going to land right there when we take that z value. Everybody follow? But again, it's set in stone, isn't it? So you can walk through it. So the first step is what? What's step number 1?
State the null and alternate hypothesis.
Very good. State the null and alternate hypothesis. So when you're stating that null and alternate hypothesis, what are you going to have every time? Let's use the mean again. This one is going to be what? 3 options.
Greater than or equal to, less than or equal to, or equal to.
Greater than or equal to, less than or equal to, or equal to, isn't it? One of those 3. And then whatever number. Right? So when you get that, what are you going to be able to tell instantly?
Your bone's gonna be less than, greater than, or not equal to.
Very good. You're going to be able to tell whether you have a one-tailed test or a two-tailed test.
Oh, yeah, that's it.
Right? And you're going to be able to tell what?
What side's on?
Yeah, which way is going to be that shaded? Where's your alpha going to fall? Right? So, where's my alpha going to fall with this one?
Left side?
Over there. Pac-Man's eating towards the shaded side, right? Where's my alpha going to fall with this one? To the right side, isn't it? Pac-Man's eating that way. Where is this one going to fall? Both sides. And what do we have to do?
Split.
Half it. Half our alpha, yeah? All right. Is everybody good? What does this area under the curve always add to? In every problem we've ever done in this class? 100%. 1. Very good. Okay. Let's do an example and go to the fall fair. What do y'all think?
Fair.
Do you have another class after this one? You're not leaving, are you? Okay. I was going to say, man, come on. You sat through this much, might as well stay. For the grand finale, the example. Everybody ready?
Yep.
Okay, how many steps do we have?
6.
6 steps. Are they the same every time?
Yes.
Yes, they are. So, let's do something interesting here. I'm going to go ahead and erase this. Yep, erase that. The rest of that. And, well, if I can open my marker, I'll do something interesting. All right, so we know it's going to be a normal curve, right? Because just we wouldn't be doing this. There would be no reason to live if this weren't a normal probability distribution.
That's true.
Now I'm going to leave this here because I know what kind of problem we're doing already, right? Because we're in this chapter, yeah? So I'm going to leave that right there because I know we're going to be using an average, yeah? So that's easy. I've already set up a little bit of it, haven't I? And I haven't even looked at anything. I haven't even looked at the title of the problem. What does the title say?
James and Stewart.
No, the title.
Two-tailed test example.
Two-tailed test. Well, that tells me something right there, doesn't it? What does that tell me?
You can put your alphas on both sides.
Very good. So that two-tailed test tells me that I'm going to have this shaded over here, aren't I?
No, you don't know your significance.
And what's this line right here called? Critical
Your CV.
value. Very good. CV.
I was thinking of CV actual, but it works. So makes me happy.
What else can you tell though? If you know that I have areas shaded on both sides, what is this going to be?
Equals to equal.
Very good. That's going to be an equal sign right there, isn't it? Because that equal sign means that I'm going to have both sides shaded.
And your alternative is going to be not equal.
And very good. And my alternative is going to be not equal. Why is that?
Because it's opposite.
That's the opposite of equal. If this equals something, anything else is going to be not equal to it, right?
And that's all we have.
No, it's not either. Two-tailed test example. What is after that comma right there?
Sigma known.
Sigma known. What does that mean? Sigma. What is sigma?
That is your population standard deviation.
And that's important in what we've been studying. So what does that mean? What does that sigma mean?
We're going to be using z-score.
Very good. We're going to be using the z, aren't we? Sigma z, st, right? But if you see that sigma, we're using a z-score in this class, all right?
Pretty nifty little round.
So wait, what's my formula for the z-score? Who remembers?
Be
X bar minus what?
minus your.
Mu, very good. Population mean over what?
Your sigma
Divided by what?
Square root of n.
Very good. Sigma over square root of n. What is that called? Sigma divided by square root of n.
The standard error.
Standard error. Teams, 1 point, extra credit. Send me an email.
Yeah, got you.
Good job. Standard error. Does everybody remember that? Okay. Wait, did you get it tattooed?
Nah,
And you still remembered it?
yeah.
Listen to this guy.
That's not 1.5 extra credits right there.
Huh?
Keep going.
No, I'm just making sure I don't have to pay for any ink, dude. I mean, invoice the business office. All right. I'm sure they'll pay it promptly. All right.
Some picture of it. Oh, your rumpus.
So what variables can we solve for right here? What do we have to solve for in order to solve this? Well, that one,
Yep.
that one, that one, and that one. Oh, here's some more good news. Everything's going to be given to you in these problems. You're not going to have to solve for nothing. Told you, the math is easy. The hard part's setting them up, like we're doing right here, okay? All right. So that's going to equal something, that's going to equal something, that's going to equal something, that's going to equal something. Oh yeah, what's that other variable we have now? That's, huh? No,
No.
that one, isn't it?
Oh, you're right, yeah.
Yeah, the alpha, that new one we learned about. Okay, so what else do we know about this problem? Well, that might be about it, but I mean, we've almost solved the thing, haven't we? And we haven't even looked at the problem yet. That's just from the title. We've solved all this stuff.
And these are numericals now.
Yeah, now all we gotta do is plug in some numbers and we're done. So the big two things we're gonna have to do is what? Solve for the z-score and compare that z-score to the critical value. To see whether it falls to the one side or the other of the critical value. And then what's another thing we're gonna have to do? Find the critical value in the table. And that's really it, okay? And be able to tell what it's telling us. All right, so the Jamestown Steel Company manufactures and assembles desks and other office equipment at several plants in New York State. At the Fredonia plant, the weekly production of the model A325 desk. Where does A325 plug into this thing?
It stays right there in the description.
Very good. It's not a number that we're going to use, is it? But again, don't let that kind of junk throw you off. They just try to unnerve you. All right. Follows up normal distribution. But hey, we already knew that. That's why we're here, right?
Yeah.
Okay. With a mean of 200.
Right there.
Sounds like a number.
Go down 4.
Or, no, what? Is that my sample mean or is that a population mean? Did we take a sample of anything? We didn't.
No, that should just be your population.
That's right. That's just what's going on in our plan, isn't it? We've been making these suckers for 30 years. For 30 years, we've been doing the same thing, and we know that it's 200 a week. Okay? So that's our population. Our population mean. Oh, down 4. I see what you're saying. Okay. 200.
I'm not that down. Almost. Not quite.
All right. Blah blah. Follows a normal distribution with mean of 200 and a standard deviation of 16. So what is that? Is that our... Very good. That's our sigma, isn't it? That's our population standard deviation. Because again, we've been making these things for 30 years, let's say. I'm just making up the 30-year part. But we know that every week we make 200, and 68% of the time we're making between 216 and 184. Right? Okay. So what did I say, 16? All right. Blah, blah. New production methods have been introduced, and the Vice President of Manufacturing would like to investigate whether there's been a weekly change in production of the model A325. So some smart college grad that thinks they know everything from Dalton State has come to work over here, and they insisted that we install new equipment, and they want to see if there's been a change in that 200 a week. Okay? So, what would we do Are we gonna look at the whole population? What do we usually do when we want to study a population? We take a sample. Okay, but we've been at this for 30 years, all right? So we're gonna take a sample. Actually, we'll get to that in the next slide. The way this problem breaks it up is weird, okay? But, so we have these new processes. We changed the way we do them, right? And we want to know, is the mean number of deaths produced different from 200 at the 0.01 significance level? 0.01 significance level is what? Well, what is the significance level? It's our alpha, huh?
Yeah.
0.01, isn't it? Very good. So now we know something else about this curve, don't we? So if our alpha is 0.01, the alpha is the shaded area, isn't it? So what do we have to do with that 0.01? Very good. We got to divide it in two, don't we? So this is alpha over 2, and this is alpha over 2, isn't it? Which equals what? 0.005, isn't it? 0.005. All right? So it makes sense that if we do all our math and our z-score falls out here somewhere, there was only a 1% chance that it would have fallen out there if our population, if our null hypothesis is correct. Yeah? Oh, by the way, that's something else what did we say our population mean? What's our null hypothesis? That what? What is the standard status quo? What is going on in our business? The mean number of deaths we produce equals what?
200.
200 every month. Okay? And what would our alternate hypothesis be? 200. That it doesn't equal 200. That's all we got, yeah? It's either 200 or it ain't. All right. So step 1, state the null and alternate hypothesis. Boom, we just did that, didn't we? Pretty easy. How did we do that? How did we get that data? We did what? Read the problem, didn't we? And we plugged it in. All right? Step 2, select the level of significance. Well, here it's going to be 0.01. Where did we get that from? It was in the problem. It told us right there. At the 0.01 significance level. Well, so far this is kind of boring, isn't it? Because it's just too easy.
Yeah.
All right. Step 3, select the test statistic. In this example, we'll use Z. Why are we using Z?
Because your sigma is not.
Because we know our sigma, don't we? We know our sigma. We don't have to estimate our standard deviation. We know what it is for that population. So we're going to use the most accurate we can, that Z-score, huh? All right. So now we're really going, aren't we? We're already halfway through. Oh my gosh, I'm almost embarrassed to do this. This is so easy. All right. Formulate the decision rule by first determining, so let's determine the critical value. All right, this could be the only little kind of tricky part, but we just got to figure out what this is, don't we? Where this line is. It's going to be the same on both sides because we're interested in the middle part. All right, so this right here, it's a Z value of 0, isn't it? Okay, so this is going to be like 1 or 2 something probably, if I had to guess. You know what I mean? Because they're those Z-score looking things. All right.
It's 2.576 possibly.
Well, where did you get that? First, we got to look it up somewhere. Where do we need to find this critical value from?
On our table. Or
Okay. So, what area are we going to look up on the table?
You're going to want to do.
If this, what? 40 what? 9 point what? Percentage.
Yeah, it'd be.
If this is half a percent, huh?
49.5.
Very good. Where did you get 49.5%? This is how much in a percentage instead of the 000s.
0.5%.
This is 0.5%, isn't it? Move the decimal place over 2, you got 0.5 of a percent. No.
You look for 0.495 on your chart.
Very good. So this is what percentage? 49.5%. Where did I get that from? 49.5% plus 0.5% equals 50%, doesn't it?
And it's the same for the other side.
Same for the other side, isn't it? This is exactly what we've been doing the whole time, isn't it? We've been doing this for a while, haven't we? So 49.5%. So we move that decimal place over and we got 0.495. Now, let's go to the table real quick. And where's that going to fall?
Find the 4 9s.
4, 1, 4, 1, 4. Oh, here's 4, 7. Remember that one we were using all the time? 1.9 what? 6. Remember, we're not doing that right now. Okay.
There's some 4 9s.
So here's my 4 9s. 4979. 4979. Notice the difference gets smaller each time as we get up here, doesn't it? Anyway,
Go up about 4 numbers.
here's 4986. We're looking for what? 49 what?
4 9 5.
5, aren't we? So here's 49, 496, 4948. That's close. 4949, 4951. So we're right in between these two, aren't we?
Bingo.
So let's look at 2.5. Bring that over to here. And then let's take it up. So 2.5 between 7 and 8. So let's say 2.58. Yeah, round it up to 2.58. What do you think? 2.575, round it up to 2.58.
It's a good number.
So that's 2.58, and that's 2.58. Plus and minus, right? Okay, but I'm still missing a couple of variables here, aren't I? To be able to solve for this thing. Because we got to solve for this and compare it to that, don't we? To see if it falls in the shaded area or not, okay? So fortunately, what did they say? 2576, 258. Okay, so we just rounded it up, didn't we? Okay. So fortunately, we got a little more information in this problem, okay? You ready? So we're already at step 5. We're going to take the sample, and we're going to compute the test stat and make a decision. So they mixed them up a little bit, but it's still the process, okay? So the mean number of deaths produced last year, so that's our sample, okay? 50 weeks. Because 2 weeks were closed down for maintenance, okay, and vacation, all right? So 50 weeks last year, we produced 203.5 desks, okay, per week. All right? That's our sample, because that's 1 year out of 30, okay? And that 1 year out of 30, we had a sample size of what? How many weeks? 50, very good. So that would be what? The N right here, wouldn't it? And what's the average we came up with?
203.5.
So for that 1 year, that average of 50 weeks, we came up with 203.5. Hey, that's different than our population mean, isn't it? What have we always thought it was?
200.
200, but we came up with 203.5. But let me ask you something. Every time we've been taking one sample, just one sample out of a population in this class, does it ever fall right on the population mean? It doesn't, does it? It's always off. My question is this off enough for us to be able to say, hey, we're rejecting that null hypothesis. We have a whole new mean here. So, let's plug these numbers in here. Where's everybody going? It's not time yet, is it?
Yeah, it's 2 minutes after.
Okay, let's do this quick. Z equals what? X bar is what? 203.5 minus what?
I'm not sure. 200.
Minus 200 over what? The standard what, Peyton?
Error.
Very good. Another point. No, I'm just kidding. You only get one a day. Sigma is what?
16.
16 divided by the square root of 50. And that's going to give us an answer of 1.547 in this case. 1.547. 1.58. So 1.58 rounded. Where's that fall on here?
Right about there.
About right here, isn't it?
Yep.
Positive 1.58. Are we going to reject this null hypothesis or not?
Nope. Where you going?
We are not going to reject the null hypothesis, are we? We cannot say that our average is definitively different from that 200. It fell within this reasonable average. If our null hypothesis is true, we came up with a sample and plugged it into the z-score formula, and the z gave us a number right here. It's very much within the realm of possibility that that sample represents a population average of 200. Okay? Does everybody follow me? Okay, is everybody good? All right, be looking for your assignments for this chapter and the practice exam.